Yep, perfect, Esther. She just turned it on. Thank you. And we'll have time at the end for questions from the participants. We're using Teams webinar functions, and as such, your microphones and webcams have been disabled. We ask that you utilise the chat function within Teams to ask questions along the way, and Mohsen and I will answer them at the end of the webinar. So firstly, I'd like to introduce myself. I'm Simon Zander, the Head of Sales for Adasa in Australia. I've been working in the water industry for more than 25 years, doing everything from design, maintenance, operations of water networks and treatment plants. I'm a civil engineer by training, and I worked for a water authority in Australia called Hunter Water Corporation. And at Hunter Water, I was actually a dam safety engineer for the two large dams that they own, called Chichester and Grahamstown Dam. Now, I'd like to welcome Dr. Mohsen Askari, our Senior Data Scientist in Adasa, Australia. So welcome, Mohsen.
Thanks, Simon, and hello everyone from Australia. I'm Mohsen Askari, a Senior Data Scientist at Adasa. I have a PhD in Mechanical Engineering, and I have worked in the area of structural safety and health monitoring and damage detection for about 10 years. I'm also a guest lecturer at a couple of universities in Sydney, Australia, and I hope you guys enjoyed this webinar.
So some of you may know that we did a webinar about 6 weeks ago, and we touched on the digitalization of assets. And the digitalization of large civil assets is happening quite quickly through the use of different technologies, be it traditional instrumentation, IoT, or satellite technology, or automated surveying equipment, for example. However, as the graphic on the screen shows, digitalisation is not just utilising new technologies, it's about the people and the processes that are also utilised. So to truly get the benefits of digitalisation, we need all three elements: technology, processes, and people. While artificial intelligence and machine learning are buzzwords that are very common in today's world, AI and ML have been around for more than 50 years. AI and ML have been used to solve problems in the physical world previously and continue to do so. Mohsen, can you give the audience some background on how AI and ML is utilised to solve problems in other civil structures?
Definitely. As you mentioned, Simon, AI and machine learning have been around for a couple of decades already, and they have been also widely used in civil structures such as bridges, buildings, towers, and they are mainly used during demolition and construction, and also the post-construction of those structures to detect any damage, and also for the vibration control. Examples are, for example, the Sydney Harbour Bridge, where 2,400 sensors are installed to continuously collect the response of the bridge to different loads, such as traffic load or wind loads. And then the data are processed and analyzed using several AI and machine learning techniques to find out if there are any anomalies in the bridge, so they can go and close the bridge and do further investigation. Another example is Burj Khalifa in Dubai, where AI and machine learning algorithms such as fuzzy systems, neural network, and decision tree systems are used for controlling the vibration and damping the vibration of the structure and the vibration of the tower using and via some control devices such as dampers. There are some other examples of application of AI and machine learning in mining, roads, smart cities, transmission towers, telecommunication towers. But today we want to look at the application of AI and machine learning in dam safety management. And I guess this is something that Simon you are quite familiar with and you have worked in this area before. So maybe you can tell the audience about how dam safety management is conducted and some of the current challenges.
Yeah, thanks, Mohsen. So I guess dam safety management is a complex task, and there's a lot of different systems providing the data that dam safety engineers need to make the decisions about operations and maintenance of these long-lived structures. So as we've talked about before, many of these systems that inform the dam safety engineers can take months between when the data is collected and when it is analysed. And as you can see from the graphic, some of the failure modes can't wait months between when the data is collected and when it is analysed. So we've previously spoken about a solution that some dam owners are utilising to improve the time between data collection and the analysis of the data. And that solution is called Dam 360, and we'll talk a little bit about that at the end of the webinar. However, the focus of this webinar is really on what we can do with the data when it is centralised in one place. So even when we get the data into that one spot for future analysis, there are many questions that need to be answered about items such as, is the data reliable? Is there too much data? Have we got the right alarms? Do we have too many alarms? And what is anomalous behaviour? So, and ultimately what we're trying to answer, is the dam safe? And what we'd like to share with you now are some ideas around utilising artificial intelligence and machine learning to help you with these problems. So Mohsen, can you go through some of these ideas, please?
Sure. The overall idea is not very complicated. We first need to collect data from all the manual and telemetry sources. These data could be seepages, uplift pressures, pore pressures, movements of the dam, shifts, tilts, and these are called, we call them like independent values and independent parameters. And then we also need to monitor the storage water level, tailwater level, temperature and rainfall, which we call them basically, these are independent parameters. And the response of the dam to these independent parameters are called dependent variables. Then what we need to do, we need to find the relationship between these parameters, the independent variables and independent variables. And for example, how uplift pressure is correlated with the storage water level, or what is the relationship between the seepage and temperature, rainfall, and storage water level. Once these patterns and relationships are understood, then we can predict these measurements and define thresholds. So when new data comes, we can compare them to the thresholds and to the predicted values and decide if it's showing, the dam showing an unusual behavior or not. So we can raise the alarm, and in that way, it can help us to make the decisions better. We have actually developed several algorithms based on AI and machine learning, and we applied them to 18 different dams in New South Wales, Australia. Here you can see some of them. These are some of the major dams in New South Wales of Australia, and they are mostly gravity and embankment types of dams. So the first step that we need to do is actually cleaning the data. Well, there are actually lots of techniques that can be used to clean data for modeling and analysis purposes. Here are some examples of how the initial raw data of pore pressures at different section of the embankment of a dam in New South Wales look like. And after we applied the cleaning methods, such as the local outlier factor, it looks like this. Sometimes we also need to deal with the missing data, but we can also handle it using very simple techniques such as the interpolation, linear interpolation, or some more advanced techniques such as k-nearest neighbors. But anyway, having good and clean set of data is essential for modeling and setting up the thresholds, such as the semi-static threshold, Simon.
Yeah, I guess most people understand the concept of data breaking a threshold to provide an alert. However, what if that threshold is not applicable under certain circumstance? Let's explore this concept of semi-static thresholds. So Mohsen, can you explain a little bit further, please?
Well, dealing with different dams and the way the data of those dams are traditionally analyzed, we found that dam safety engineers mostly use one single number, which is called static threshold, to determine if a measurement is normal or not. For example, if most of the historical seepages are below 20 liter per minute in the last couple of decades, then 20 liter per minute is considered to be the threshold. The issue, however, is that that single number is found by looking at the historical data of that measurement without considering the effect of a storage water level or temperature. It means if the storage water level is low, but the seepage is at 16 liter per minute or 19 liter per minute, for example, these points here, they will be like normal because they are still below the 20 liter per minute. A quick and simple fix to this issue is to divide the storage water level into three range of low, medium, and high, and also the time of the year into 2 times of hot and cold, and then define a threshold for each of these 6 regions using some simple statistical methods such as Tukey test and box and whisker plot. And in that way, instead of dealing with one single threshold, we are working with 6 different thresholds for 6 different regions. That's why we call it semi-static threshold. The results are very, as I said, the method is very simple, but the results are very good and very great, because now, as you can see, the orange line, which is basically or a static or semi-static threshold, is more adapted to the distribution of the seepage. And those points that were initially below 20 liter per minute, and however, it's different from the surrounding points, are now well captured by this semi-static threshold. This is just another example. However, if you want a more dynamic threshold, as you can see here, it's like very much a step-like threshold. There are only 6 numbers, but if you want fully understand the relationship between the seepage and other parameters, or uplift pressure and other parameters, and then define a better threshold which is adapted to all the conditions and all the situations, then we need to develop predictive models and then define the dynamic thresholds. And we did it for uplift pressures and pore pressures, shifts, tilts, and movements of the dam, and also the seepages. For example, to predict the uplift pressures, we know that hydrostatic loads are the main parameters that affect the uplift pressures. However, the age of dam is also important. It means the uplift pressure in 1st of July 2022 compared to 1st of July 1992 under the same hydrostatic load might be different. And that's because of the aging of the dam, because hydrostatic load is same, but numbers are different. So, well, dam aged, or maybe sensors aged. That's why we chose both the hydrostatic loads and the aging terms to predict the uplift pressure and pore pressures. We used some methods such as the MLP neural network, the multiple linear regression. This is the famous one. Civil engineers call it hydrostatic model. Random forest regressor or support vector machine regressor, and these are the inputs that we define. And then these are the results. The blue line is actually the real measurements, and the orange one is the predicted values. Using the error between the predicted values and the real measurements, we would be able to define and set up the thresholds, which is the green line here and here. To predict the seepages, however, we need to do a little bit more because it's more complicated. It's function of different parameters. Also, we notice that sometimes there is a delay between seepage and other parameters. For example, storage water level is increasing and then seepage is increasing as well. But if storage water level starts to decrease, we notice that seepage is still increasing. And that's because of the delay, because delay between the seepage and the storage water level. So that's why we considered several potential inputs to build a predictive model for seepage, including the hydrostatic loads of not only today, but also the previous days, rainfall and temperature of today, as well as the previous days, together with the aging terms. We used several algorithms and several methods, such as the neural network, the HSD model, and the support vector machine regressor, and we combined them with some feature selection methods. Why? Because we defined a lot of inputs, but not all of them are actually important, and not all of them are needed to build a concise but accurate model. So we needed to pick up and find some of the most important inputs. That's why we used principal component analysis method, or a stepwise regression method, or the random forest to select the best features. Here are some of the examples. So the black ones, the black dots, are actually the real measurements. The blue ones are the predicted ones, and the red ones, red one is actually the threshold. This graph here shows the performance of the algorithm using different number of inputs. So if you look at it, you will notice that if you use only 4 inputs, you get almost the maximum accuracy which is possible to get, right? And those inputs here are mainly the hydrostatic loads, storage water level to the power of 2, to the power of 3, and to the power of 4. But maybe for another seepage point, the number of inputs and type of inputs that you get is different. So here, those 4 inputs that we picked to build a predictive model are basically hydrostatic loads, some of the terms in the hydrostatic loads, including the storage water level power of 4 and power of 3, and also the aging terms, which are basically the age of the dam and also the natural logarithm of the age of the dam. But Simon, these predictive models are not the only tools to raise alarms. We did also more things.
Yeah, so Mohsen, I guess with that predictive data, what do you do to help make decisions after you've got that predictive data? Can you show us what are the next steps to help make decisions about when to do further work on an asset or to intervene?
Of course. The other method that we found it to be useful is the rolling correlation, is the concept of rolling correlation. And we used it to find out if the trend of a measurement over years is changing or not. For example, let's talk about the seepage. We know seepages are mainly a function of a storage water level, right? Now, if I define a moving 6-month window and calculate the correlation between the storage water level and the seepage inside this window while it's moving, and then mark all those scores in a plot, I get like these figures. These are the rolling correlation plots. These are basically the rolling correlation between the seepage and the storage water level. So we have 3 plots here for the 3 different seepages. As I said, we expect that seepages are quite responsive to a storage water level, and they have a strong correlation. Sometimes we notice that, okay, that correlation at some years or at some month is very weak, and it's even negative. It means that it's totally irresponsive to the storage water level. When we looked at these 3 seepages at 3 different points of 3 different locations of the dam, we noticed that they are actually happening at around the same time. When we talked to the dam safety engineers, they said that, okay, at that time, there was actually a major maintenance going on in the dam. So it was interesting that we could see that effect in the in our data analysis.
Thanks, Mohsen. I guess we did this webinar earlier on, and one of the questions was, do we get feedback from the dam owners about the performance of the dams when we do these analyses? And it just goes to show you do need to be in discussions with owners to give you insights about what's happened to the dam over its life. When major maintenance has been done, the dam will perform differently. And that was certainly the case in that analysis. So, but I guess we're going to move into outliers. Everyone's heard about the term an outlier, but how do you actually detect an outlier in a large data set?
Well, it can be quite complicated and complex, but AI and machine learning offers some tools and some algorithms that you can pick up the outliers among large data sets. So the idea here is to put the measurements from the gauges from same type and same location of the dam. For example, here are all the uplift pressures from upstream to downstream at one block on the dam, which is, in this case, that block was located at the center of the dam. And then we used a method of outlier detection called local outlier factor. What it does is that it put these 3 measurements together and then try to, let's assume a 3D space with 3 dimensions that each of them indicate each of these uplift pressures. And then it tries to cluster them in this space. And then if any data point fall basically outside of these clusters, then they will be picked as an outlier. In another word, we're looking at this moving window. This moving window is 3 years. So if the data point that we're collecting today is not following the same pattern of the data points in the last 3 years, then we could raise an alarm. Example here is that, for example, after 2014, in this case, we noticed that the green uplift pressure is exceeding the orange and blue one, which was not the case previously before 2014. And immediately the algorithm could pick it up and dam safety engineers could receive an alarm. Here are actually a 2-dimensional space. We plotted the uplift pressures versus each other, 2 uplift pressures versus each other. And you could see that each algorithm divides all data sets into outliers and inliers. Here we are actually using different algorithms, not only the local outlier factor, but also some other algorithms, such as the average KNN or feature bagging or one-class support vector machine here, or the principal component analysis. So we have applied different algorithms to the same data set, and we noticed that there are points that are picked up and flagged to be an outlier using the majority of the algorithms. But then we have some other points, some other data points that are only detected to be an outlier in 1 or 2 of the algorithms. Therefore, we thought to be on the safe side and to be also a little bit more conservative, we combined several algorithms together, and we're looking at the performance of these algorithms at the same time. So if a data point is identified to be an outlier using the majority of the algorithms, so we can safely say that it is an outlier and we can raise an alarm. That way, well, we can also prioritize the alarms, which is, I guess, a subject that you are quite familiar with, Simon.
Yeah, thanks, Mohsen. I am familiar with alarms and alarming techniques. I have a background also in monitoring systems and asset management. And I guess setting the correct alarm level is extremely important to reduce risk and to ensure that customer service levels are at the highest they can be. I guess a simple method to set an alarm is a threshold that we talked about earlier on. But you can also do more complex methods where there's two thresholds. So if one threshold is broken, it can be a lower priority alarm. But if both thresholds are broken, it is a higher priority alarm, a bit like a joint probability.
And the other one is looking at the different number of gauges and different gauges that are located in the same location. Let's say, for example, at block 4 of the dam, at the center of the dam, we are measuring all the uplift pressures from upstream to downstream at 3 different points. If these 3 gauges, all of them are showing anomal behavior and all of them triggering the alarm, so we can send a high priority alarm to the dam safety engineers, while if only one of them is showing anomal behavior and unusual behavior, we can send a low priority alarm and we can wait to see what will happen in the next couple of hours or in the next day.
And I guess the third methodology that we're proposing here is a bit like a fault tree, where the measurement of alarms is linked to a failure mode. So if a failure mode with a high consequence, if an alarm with a failure mode of a high consequence is triggered, that alarm becomes a high alarm. Similarly, if a lower consequence failure mode alarm is triggered, it becomes a low consequence alarm. However, this methodology takes a lot more work to actually utilize, and it takes expertise from people who have understanding of the failure modes of a dam and linking the instruments that can measure those failure modes. We're actually working with one of our clients in Australia on doing some work to link the instruments to the failure modes at the moment. And we are getting some expertise from some expert geotechnical engineers. So what about the vibration of a structure that we're looking at? And I'm not just talking about vibrations that might be induced by earthquakes. I'm talking about the natural vibrations of the structure. And so, Mohsen, can you explain this concept a little bit further?
Definitely. Well, monitoring the vibration of any civil structure is quite important because it gives you tools and options to uncover many characteristics of the structure, such as mode shapes and natural frequencies of the structure and even damping, and find out some of those potential issues and damages inside the body of the structure that might be visible after some years. With the dams, unfortunately, it's something which is sometimes ignored, and there are not many works reported on this one. In our practice, and when we were working with our clients, we noticed that in one of the dams in New South Wales, they had recorded all the acceleration signals at 3 different points of one of the dams, A, B, and C, from the crest to the foundation between 2015 and 2017 using some wireless accelerometers. So they gave us access to the data, and we analyzed their data, and we could be able to find out the natural frequencies of the dam in different modes. So here is the natural frequency of the dam in mode 1, mode 2, and mode 3, and here is the profile of a storage water level. It's interesting to see that when storage water level is decreasing, the natural frequency of the dam in all three modes are increasing. And when you have a jump in the storage water level, you have a drop in the natural frequency of the structure. The other interesting thing is that with the change of a storage water level, the lower modes, the frequency at lower modes does not change as much as the natural frequencies of higher modes, such as mode 2 and mode 3. So how can we use this? So tomorrow we go and inspect and measure the storage water level. Let's say it's at 115 meter. So if the storage water level is at 115 meter, we expect that the natural frequency of the dam in the third mode is around 3.5 hertz. If the natural frequency of the dam is at 3 hertz, then it means that there is an issue and there is we need to go and investigate. However, if we have more accelerometers along the crest of the dam, from crest to foundation and from upstream to downstream, we also be able to say where is that damage is located. And that's the benefit of using accelerometers in these structures. We have not done all these algorithms and these techniques on papers and only, but we also implemented some of them into an app that Simon, you mentioned earlier about DAM 360. Maybe you can talk about our app DAM 360 that Adasa designed. I guess Simon.
Oh, sorry, I was muted. Sorry, thank you. Thanks, Mohsen. So DAM 360 is actually two apps and a web portal for analysis of data. So the two applications are basically available to use on mobile telephones and tablets. And the first application is called the Management app. And the Management app allows a dam safety engineer to set up routes and instruments to collect, and also to collect information from existing telemetry and other IoT type instruments. That application then provides a route for someone to utilize and do the collection of data. So if you're doing a daily collection, you will follow the route that is being set up by the dam safety engineer to read the instruments and to read different conditions of the dam, including taking photographs and entering information about the condition that you find. So within the app, there is also some important features, including bounding the data so that data is not collected outside of the boundaries of the instrument. And we can also ask people to confirm that the readings are correct if the data that has been input is slightly outside the ranges that we expect or from the previous history. And this goes to the point of ensuring that the data that is collected properly in the first instance. So the app can work with mobile phone coverage or without, because we know a lot of dams are in black spots. They're in remote areas that don't have mobile telephone connections, or you may be in a gallery of a dam where you do not have connections at all. So the third part of this DAM 360 suite is the actual analysis platform. And the great thing about what this DAM 360 provides is, as soon as you do you upload that data, the data is available for the dam safety engineer to analyse. And the platform allows you to do the analysis that a lot of the analysis that Mohsen is talking about. And we have implemented some ideas into there, such as the semi-static thresholds. Our customer, Water New South Wales, is using this application, and in fact, they wrote a paper at the Australian National Committee on Large Dams, or ANCOLD, in 2019 that claimed a 15% risk reduction by utilising this platform. It's the first time that we know of that a dam owner has been able to reduce the risk of owning a dam without doing any capital works. So we'd certainly encourage you to get in contact with your local ADASA salesperson to actually do a demonstration of Dam 360. And I guess we've come to the end of our webinar now, but we would like to open up for any questions. Now, I guess if you don't have any questions, oh, here we go.
I think someone just raised his hand under Salazar. I think, unfortunately, everyone needs to put their questions in the chat, and I think the mic and camera doesn't work for the audience.
We have a question, Mohsen. Would it be possible to use these algorithms to predict the movement of a dam?
We can actually, and we did it. It depends. As I said, some of the dams are basically were embankment dams, and for those embankment dams, prediction of the, for example, the settlement of the embankment or prediction of the lateral movement of the embankments are quite difficult. But for the concrete section of the dam, it is doable, and we did it, such as tilts and shifts. And also we can, by looking at the shifts and the movement of the dam in lateral direction or in the longitudinal direction, we can also tell a little bit about the future, that if a storage water level going to remain at high level, what will happen to this dam?
Yeah, yeah. There's another couple of good questions in here. How mature is the approach to be able to apply to new dams outside of the case studies that you've shown us, Mohsen?
Yeah, well, actually, these results that I showed are from different dams. So as I mentioned, we have worked with 18 different dams. So we started with the probably the most important dam in New South Wales and Victoria, which is heavily instrumented. But then we generalized that, and we applied those methods for other 17 dams across New South Wales. So the algorithms and the models are quite mature to use for any dams. There is another question from Fernando Salazar. Do you divide the data into training and testing? Definitely, this is the must, and this is the principle that we need to do that. We divided all the data into training and testing, and we validated the data using the test data as well. So we feed the model on the training data, and then we validate and we test it using the test data.
Okay, so this is another interesting one here too. Assuming that meteorological data is important because of the intense participation events can trigger threshold alerts, how can the system be applied in countries with poor meteorological forecasting data? I guess that's a difficult question. I mean, the poor data is we're going to have poor outcomes, I guess. And my take on that is that we should be getting as much data into the system as possible. But Mohsen, have you got any takes on that one?
Yeah. Well, having access to a comprehensive set of data is quite important for us. Definitely, if data for any reasons are very polluted and very noisy, then to be honest, we can't do much about it. But if some of those data are missing, for example, if the temperature data is missing for any reason, or the rainfall data are missing, we could still be we still be able to analyze the data using the storage water level and tail water level. And also the other method that I showed you is purely based on the measurement, the response of the dam. We don't need the temperature, we don't need the rainfall, and we don't need the storage water level. We just look at the pattern exist between different uplift pressures. And I guess I haven't done the analysis with the very bad quality data. But I'm just guessing that if we have set of uplift pressures, for example, 4 different uplift pressures from upstream to downstream, and all of them for any reasons are noisy, we would be still remove that noise, because all 4 devices are basically are from same type, and the noise can be removed between the can be found and can be removed as well. But I would love to work with some poor data and some noisy data to see like what is the result. There is, I guess, another question. You mentioned different algorithms. Which one do you use more often? How do you select them? Okay. So if you looked at the prioritization of the alarms, we can combine different algorithms. So we talked about triggering the alarm. And if, for example, if 2 measurements or 3 measurements are triggering the alarm at the same time, okay, so that one was one of the ways that we prioritize the alarm. The other way that we can prioritize the alarm is that, let's say we have used 3 algorithms, and all those 3 algorithms are saying to us that that data point is an outlier. For example, we use the predictive model, and we found that the data point is beyond the threshold, beyond the dynamic threshold. Then we use the outlier, the group of measurements for the outlier detection, and we found that that data point, using those outlier detection methods, it's also an unusual behavior and an outlier. It also above the semi-static threshold, for example. Or from the rolling correlation, it also showing that that data point in that period of the time is showing us some unusual behavior. So that is definitely a high priority alarm. But if one data point is only above the dynamic threshold, but is not picked to be an outlier when we put a couple of measurements together to get to find the outlier, then that's the lower priority alarm. Okay,
I think,
yeah.
There's another interesting question here too. Is it wise to trust the safety of a dam to these AI algorithms? And I think Mohsen and we've spoken about this quite a bit, and we agree that AI and ML is never going to replace humans, particularly not on dam safety, such an important structure as a dam. We both agree that these are the analysis that you can get from AI and ML will help dam safety engineers with their decision making. It's not to replace engineers, it's to help. It's to give them another piece of information, and that's what we certainly propose.
Okay, I just mentioned one more thing regarding Fernando's question. regarding the selection of the algorithm and selection of the method. If there is a good accuracy in between our prediction and the real measurement, I would love to stick with the dynamic threshold. However, if the accuracy is not that great, then we can actually combine different types of algorithms.
Okay, so I think we've exhausted the questions. I really appreciate the questions. They've all been really, really good, and thanks very much for your attendance. Please feel free to contact us if any of these topics piqued your interest. And if you're interested in the AI and ML analysis of your data sets or any of the semi-static or semi-automated collection methods, and you would like a demo of your DAM 360, please contact Adasa in Spain or myself in Australia. It's harder with the time zone, but you've got our contact details there, and please feel free to reach out to us. So thanks again for attending the webinar, and thanks very much, Mohsen, for your great insights.
Thanks, Simon, and thanks everyone. Have a good day in your country.
Goodbye.